You know that feeling when you're packing a suitcase, right? You're trying to cram in all your favorite things, but you can't go over the weight limit. Well, that little headache isn't just a travel problem. It's actually a version of a famous puzzle in computer science called the knapsack problem. Today, we're going to go on a quest to solve it. And along the way, we'll uncover some really fundamental truths about how we find answers to, well, anything. So, to make this real, let's meet Knut Donald. He's a computer science student, and he's in a tough spot. He's in the middle of a big exam, the clock is ticking, and he needs 44 points to pass. He's got a list of problems he can tackle, but there's no way he has time for all of them. His knapsack is the 120 minutes he has left, and the items are the exam tasks. The question is, how does he choose which ones to do? And this is what he's up against. You can see each task takes a certain amount of time and gives a certain number of points. With 16 different tasks, there are over 65,000 different ways he could combine them. I mean, checking them all one by one, that's just not going to happen. He needs a strategy, and he needs it now. So what do? You go with your gut, right? The most intuitive way to handle this is to just be greedy. And I don't mean greedy in a bad way. I mean greedy in a totally ruthless, efficient way. You want the most bang for your buck, or in Knut's case, the most points per minute. The greedy strategy is super simple. First, you calculate that bang for your buck for every single task. Points per minute. Then you just sort them, from the most efficient all the way down to the least. And finally, you just start picking from the top of that list and don't stop until you run out of time. You're always making the best choice that's available to you right now. And get this. For Knut, it works. It actually works perfectly. By just picking the most efficient tasks first, he fills up his 120 minutes and scores exactly the 44 points he needs. He passes the exam. It feels like we found the perfect answer. Simple, fast, and it works. But hang on a second. We got an answer that worked for Knut in this one specific situation. But is the greedy strategy always the best? Is it always optimal? Or could it lead you down a totally wrong path? Let me show you just how spectacularly greedy can fail. Imagine your knapsack holds 100 kilograms. You have two options. Option 1, a single giant gold bar. It weighs the full 100 kilos and it's worth $200,000. Option 2, a tiny little pile of silver dust. It weighs only 1 kilo, but it's worth $2,001. Now, the greedy choice, based on value per kilo, is the silver dust. Its ratio is just a tiny bit better, but if you take it, you can't fit the gold bar. The greedy path leaves you with about $2,000, when the optimal choice was to just take the gold bar for $200,000. Yeah, the simple answer can be a disaster. Okay, so if the simple, greedy path can fail so badly, our quest has to continue. We need a method that will find the perfect 100% optimal solution every single time, no matter what. So let's look at two really powerful ways to do just that. First up, we have dynamic programming. You can think of this as the meticulous planner. Instead of just jumping at an answer, it patiently, carefully builds a solution from the ground up. It's like it creates a giant chart and first figures out the best possible score for a knapsack that only holds 1 minute, then 2 minutes, then 3. It does this all the way up to 120. Because it solves every smaller version of the problem first, it guarantees that when it finally gets to the end, the answer it has is provably perfect. Now, our second method is called branch and bound. This one is the clever shortcut taker. It also wants to find that perfect answer, but it tries to get there a lot faster. It starts exploring this huge tree of all the possible choices. Take this item or don't take it. But its real genius is in knowing when to give up on a bad idea. So how does it find those shortcuts? Well, at every decision point, it makes a super optimistic guess. It asks, okay, if everything goes absolutely perfectly from this point on, what's the best score I could possibly get? We call this the upper bound. It's like the ceiling of what's possible down that path. At the exact same time, it keeps track of the best actual solution it's found so far, anywhere in the tree. This is our lower bound. You can think of it as the current high score. It's the champion we're trying to beat. And here is the magic trick. If that optimistic, best case scenario guess for the path we're on isn't even better than the champion score we already have, then why bother? We know this path is a dead end. We can just chop off that entire branch of the decision tree and completely ignore it. This pruning is how the algorithm saves a gigantic amount of work.
So now we have these powerful tools that can find the perfect answer. But there's always a but, isn't there? Perfection comes at a cost, and that raises a whole new question. Is a perfect answer that takes forever really better than one that's good enough and super fast?
Remember, Knute's exam only had 16 items. Let's scale this up just a little bit. What if, instead of 16, we're trying to pack a knapsack that has 100 different items to choose from? For every single one of those 100 items, you have two choices: pack it or don't. That means the total number of combinations is 2 times 2 times 2, 100 times. That's 2 to the power of 100. And that number, it's beyond astronomical.
To even try to wrap your head around how big that number is, let's use an analogy. Imagine that every single one of those possible combinations was printed on a single, thin sheet of paper.
If you stacked all those sheets of paper on top of each other, the pile would be 14 billion light years high. That's taller than the entire observable universe. The takeaway here is pretty clear. Finding that guaranteed perfect solution could literally take longer than the age of the universe. For most real-world problems, that is just not an option. And this leads us to a really smart, practical compromise: approximation algorithms. Look, these algorithms don't promise perfection. What they do promise is to be really fast and to give you an answer that's provably good enough, like, say, it's guaranteed to be within 99% of the absolute best answer. In the real world, a 99% perfect answer that you get in seconds is way more valuable than a 100% perfect answer you can't afford to wait for. So, we've looked at simple answers, perfect answers, and good enough answers. But this whole journey into the knapsack problem, it leads us to something way, way bigger. It leads us to one of the deepest, most important questions in all of computer science and even mathematics.
This quote just perfectly captures the feeling. It's this mix of frustration and incredible ambition that computer scientists have. For problems like the knapsack, no one has ever found a truly fast algorithm that guarantees a perfect solution. But, and this is the wild part, no one has ever been able to prove that a fast algorithm is impossible either.
This right here is the famous P versus NP problem. So P is the group of problems that we consider easy, ones we can solve quickly, like sorting a list of numbers. NP is the group of problems where if someone just hands you a possible solution, you can check if it's correct really quickly. For our knapsack, if I give you a full bag of items, it's super easy to check if it's a valid solution. So we know the knapsack problem is in NP. The huge open question is it also in P? And why does this matter so much? Because the knapsack problem is what's called NP complete. Think of it like the final boss of hard problems. If you could find a fast, perfect algorithm for it, you'd basically have a master key. You could then adapt that key to solve thousands of other critical, hard problems. Everything from cracking codes and folding proteins to optimizing global shipping routes and modeling the entire financial market. You would literally change the world overnight.
And so this simple little puzzle about packing a bag leaves us staring at $1 million question. And I mean that literally. There's $1 million prize for solving it. Are some problems fundamentally, genuinely harder to find a solution for than they are to check? Is P equal to NP? Our entire modern digital world, from internet security to logistics, is basically built on a bet that they are not equal. But the truth is, we still don't know for sure. And that is one of the greatest frontiers of human knowledge.